Okay, so welcome back. And it's our pleasure to have Milen Yakimov from right here at Northeastern talk to us about root of unity quantum cluster algebras.
Yeah, thanks so much for having me at this seminar. I very much enjoyed the talk so far. I have learned quite a bit of the talks in the previous months. And thank you for having me to give a talk. I'm very excited. It's my first talk at Northeastern and at the same time being at Northeastern, so exciting first. So this is a joint work with a couple of my former graduate students, Bach Nguyen, who is at Xavier University now, and Kurt Trampel, who is a postdoc at Notre Dame. And the story that I want to tell you today about is about big quantum groups. So I want to describe a general new approach to big quantum groups at roots of unity. And this new approach is based on cluster algebras. So let me start with a brief introduction to the subject. So it was started in the early 90s by De Concini, Katz, and Procesi. And big quantum groups come in many different flavors. So they are associated to universal enveloping algebras or quantized universal enveloping algebras, quantum function algebras, homogeneous spaces, and various other classical objects. But in all these situations, a big quantum group is going to be denoted by A, has a certain natural central subalgebra, which is non-singular. And furthermore, A is modulo finite over the central subalgebra Z. So this kind of situation has been studied quite a bit in representation theory and ring theory in the 60s and 70s, and it's still going on. So there's been quite a bit of research done by Procesi, Artin, Kaplansky, Posner, Small, and many other people for this kind of situation where we have a non-commutative algebra, which is modulo finite over a central subalgebra Z. And there are many other situations in which this kind of picture appears very naturally. For instance, if you're studying representations of universal enveloping algebras of restricted Lie algebras in positive characteristic, you will encounter exactly the same picture that algebra will be modulo finite over a canonical central subalgebra that's coming from these pith powers of elements of the Lie algebra. Now, by a general theorem here, so there's some mild assumptions for this theorem, like for instance, the algebra A should be finitely generated over algebraically closed field. One can prove that every irreducible representation of the algebra A is finite dimensional. And then we can apply Schur's lemma to say that the central subalgebra Z acts by a character. So in particular, we have a map from the irreducible representations of the algebra A to the maximal spectrum of the algebra Z, where each representation is sent to the annihilation ideal of that representation in Z. So in other words, we have this geometric picture where on the bottom we have the maximum spectrum of the central subalgebra Z, and then we have fibers. Those fibers represent the various irreducible representations with that central character. And furthermore, one can actually be very precise about what those fibers are. If the maximal ideal on the bottom is called M, then the fiber is precisely representing the irreducible representations of the factor algebra A mod MA. And because of the assumption that A was finitely generated Z module, this is a finite dimensional algebra. And one of the beautiful things in this subject is that many interesting finite dimensional algebras appear as fibers of such maps. And it was one of the main ideas of Procesi from the very beginning that you can study the irreducible representations of such finite dimensional algebras not on their own, but by looking at this family of algebras, or more precisely, it's a sheaf of algebras, and by using degeneration techniques. So that's the general picture. And the results that I want to present today is that in some pretty wide generality, if you're looking at these quantum groups at roots of unity, they're actually objects of very cluster theoretic origin, where the big quantum group is actually a quantum cluster algebra, and the canonical central subalgebra is a certain canonical central subalgebra of the root of unity quantum cluster algebra, which is actually isomorphic to the underlying cluster algebra A. This was, in a sense, this is completely different from what people have attempted in the previous approaches to this kind of situation, because now we have all the combinatorics of cluster algebras, and we can look at the irreducible representations from sort of many different directions. So that will be somehow the general picture that I want to present. So let me be a little bit more precise now about the setting. So we're going to start with a symmetrizable Katsumoto algebra G. Epsilon is going to be a primitive L root of unity. L is assumed to be odd and co-prime to the symmetrizing integers for the Cartan matrix of G. So these are the standard assumptions of De Cuncini-Katz and Procesi. The UQ of G is the quantized universal enveloping algebra that goes with the Lie algebra G. And the big quantum group U epsilon of G is the Hopf algebra over Q adjoint epsilon, so the cyclotomic extension of Q, with exactly the same generators Ki, Ei, and Fi as UQ of G, and relations in which Q is simply replaced by epsilon. If G is finite dimensional, then De Cuncini-Katz and Procesi defined a canonical central subalgebra. It's a polynomial algebra in the Chevalley generators Ki raised to power plus minus L, and the Lth powers of the root vectors E beta and F beta over, again, the cyclotomic extension of Q. U epsilon of G in the works of De Cuncini-Katz and Procesi is proved to be a free module over the central subalgebra of finite rank. So in other words, it defines a bundle of algebras over the maximal spectrum of the central subalgebra Z epsilon of G. And for instance, if you want to study the Lustig small quantum group, that is just a very special fiber of this bundle of algebras. It's the fiber over the maximal ideal that's generated by Ki raised to power L minus 1, and again, the Lth powers of the root vectors. So here is like an example of what Procesi had in mind before. He wanted to study not individual finite dimensional algebras, but bundles or sheaves of algebras, and use somehow degeneration techniques to understand the special fibers. Here's an example where the Lustig small quantum group is just a fiber in a bundle of algebras. Any questions up to this point? I was told that I should stop because on the internet it's so easy to talk and to finish for 5 minutes. So I'm not going to take 1 hour, but I'll take 10 minutes the way everything is going. Very good.
Milen, can you
yeah.
Sorry, it's a very basic one. So here there's divided powers have no role in the story as you presented it.
No role at this point. Divided powers, yes. It's because we, in a little while, I will describe in how the root of unity quantum algebras appear as specializations, and we're going to be using the dual integral form, which is without the divided powers. So it's coming sort of very soon, and no divided powers here because they're somehow producing different objects. So now we're going to be interested in the general case where G is a Katsumoto algebra. And inside the quantized universal enveloping algebra, we will define a family of subalgebras, which was simultaneously defined by De Cuncini-Katz Procesi and also by Lustig. They're called quantum Schubert cell algebras because one can view them as quantizations of the coordinate rings of Schubert cells in a very explicit way. They're defined in a very simple way. We take the negative part of the quantum group and the positive part of the quantum group. we act by the braid group generator corresponding to a while group element. And the statement is that this is a finitely generated algebra over the field of rational functions in Q. And it's generated by certain root vectors, f beta 1 through f beta n, where the formulas for beta k are the usual formulas. And here beta k, of course, are precisely the roots of the nilpotently algebra n minus of w, which is the negative, the nil radical of the negative Borel intersected with w applied to the nil radical of the positive Borel. So people just think of this as a sort of quantized universal enveloping algebra of this nilpotently algebra n minus of w. Integral forms. Now, in order to formulate precisely how our roots of unity appear in this situation, we're going to use the dual integral form. That's the one that we do not divide the powers of the Lustig root vectors. So first of all, we look at what are called dual Pbw generators, and there's certain rescaling of the original generators, f beta k. And then we define an integral form of our algebra. So remember that this algebra was defined over the field of rational functions of Q. So here we define an algebra over Laurent polynomials in Q with coefficients in Z. And this is simply the subalgebra generated by these Lustig root vectors. And the integral quantum Schubert cell at the root of unity epsilon is Z adjoint epsilon algebra, which is simply the specialization of the original one. And here we divide by the ideal generated by the cyclotomic polynomial. The idea is that we really want to divide by Q minus epsilon for this specialization. However, epsilon is not an element of Laurent polynomials in Q with coefficients in Z. The minimal polynomial of epsilon is the cyclotomic polynomial, and that's how we get this algebra. Perfect. So now, to be very precise, De Concini, Katz, and Procesi define the central subalgebra of this algebra, which is a polynomial algebra with coefficients in Z adjoint epsilon in the variables in the generators in the Lth powers of the dual Pbw generators, f beta 1 prime through f beta n prime. Small thing here, just to remind you of algebra 2. One fact that you probably remember from algebra 2 is that Z adjoint epsilon is precisely the ring of integers of the cyclotomic field obtained by adjoining epsilon to Q. So the quantum Schubert cell algebra is a free module over the central subalgebra of finite rank. And in this particular picture, I will use in order to illustrate the results for like how cluster algebras actually fit into this and how all these objects can be viewed from cluster theoretic perspective. We will prove that this quantum Schubert cell algebra, this root of unity, the integral form, is a root of unity quantum cluster algebra, and Z epsilon is nothing but the corresponding classical cluster algebra. And the other thing is I will talk a little bit about discriminants and give an explicit formula for the discriminant of the non-commutative algebra over the central subalgebra. Any questions? So the next thing that I want to do is provide a sort of a general introduction to cluster algebras. Of course, I know that you have all heard about cluster algebras and you know a lot more than this and you work on those kind of objects, but I wanted just to summarize ideologically what is going on. So usually an algebra is defined by generators and relations, and Fomin and Zelevinsky thought that that's not at all helpful when you want to study basis of those algebras. And usually you need to know basis of those algebras because you realize representations of various Lie algebras and Lie groups in terms of subspaces of those algebras viewed as coordinate rings on some varieties. So what they thought is, let's think of an algebra that is generated by infinitely many copies of polynomials of algebras inside of it. And those infinitely many copies of polynomials of algebras inside of it are not arbitrary. They're related to each other by a simple procedure where we simply replace one of the generators with a new generator. And this generator is called yk prime. So it's equal to a monomial plus a monomial in terms of the original generators divided by the generator that was replaced yk. And there is a lot of combinatorics here that goes into what do we do with these monomials. So that's kind of really a complicated side of the picture. But the general idea here is that these monomials are co-prime to each other. They're also co-prime to the denominator. Furthermore, in order to actually be able to realize various coordinate rings in this fashion, we want to declare certain variables as frozen and not mutate them. And that gives us a more flexibility, which is crucial in showing that various coordinate rings actually have the structure of cluster algebra in this setting. So the next thing I want to be actually more explicit about what are exactly those monomials, because there will be certain key point here. So first of all, when we define a cluster algebra, we start with a bunch of independent variables, y1 through yn, in a rectangular matrix B tilde, and we call that a seed. And when we mutate the seed, we replaced one of them with a new variable, yk prime. And this new variable yk prime is equal to 1 over yk. We saw that on the previous slide, times a monomial plus a monomial. And now those monomials are actually very concrete. They're coming from the corresponding kth column of the matrix. We're picking up the positive entries and making up one monomial out of that, and then picking up the negative entries and making another monomial out of them. The cluster algebra is the subring of the field of rational functions in the original generators y1 through yn that's generated by all cluster variables in all seeds. And the upper cluster algebra is going to be an intersection of Laurent polynomial rings. But because we have that extra flexibility that we don't want to mutate those variables yn plus 1 through yn, we do not want to invert them in forming this Laurent polynomial ring. So in a sense, they're a mixture of a Laurent polynomial ring and a polynomial ring over the integers, and we take that the intersection over all seeds. And this is our upper cluster algebra. And let me just wait for the, and the Laurent phenomenon of Fomin and Zelevinsky is a very important result that has lots of consequences. And that result is that the cluster algebra is always sitting inside the upper cluster algebra. And there are many situations in which one can prove that these are actually equal. And we will see that in this particular talk, we will see one application of equality, but there are many other applications. So if it happens that for a rectangular matrix B tilde, these two things are equal, that plays a crucial role later in studying the cluster algebra. Next, I want to tell you about quantum cluster algebras. They were defined by Berenstein and Zelevinsky in 2004, and they're defined in a very similar fashion, but now instead of mutating everything in Laurent polynomial rings, we're going to mutate everything in quantum tori. So these quantum tori are going to be over the base ring, which is Laurent polynomials over Z in the variable q raised to power 1/2, the square root of q. The generators are again called y1 through yn, and they don't commute with each other anymore. They q commute, and the corresponding factor for the commutation is encoded in an integral skew-symmetric matrix, which we call lambda. Now, here is the key thing that is going to come up later in the talk. We want to define the mutation in exactly the same form like before. we want to divide by yk and to take the monomial of the y's that comes from certain entries in the kth column, and same thing for the other monomial. But now we have a choice. We can choose to write down y1, y2, or y2, y1, which is a certain power of q times the original product. So the idea of Berenstein and Zelevinsky was don't make a choice to go with one ordering or the other ordering, go right in the middle with the power 1/2. Because of this power 1/2, that's why we need to have q raised to power 1/2 all the time. So when you generalize this to arbitrary monomials, those are precisely the integers that you would put over here in terms of this whatever symmetrized monomials. And here is the key point now. The key point is that you want this new set of variables y1 through yn, where yk is replaced by yk prime. You want those to q commute again. And there is a certain condition that the matrix lambda should satisfy in connection to the matrix B. Remember that the matrix lambda was the matrix that shows how the y's commute with each other. And that compatibility condition is that the transpose of the matrix B times lambda is a certain diagonal, non-degenerate diagonal matrix. So the entries along the diagonal shouldn't be zero. And that immediately implies that the matrix B tilde is a full rank matrix. So in other words, if you look at the class of cluster algebras that admit quantum deformations, those will be very special ones, where the matrix B tilde has a full rank. Again, the quantum cluster algebra is defined in exactly the same fashion like the classical one. It's the subalgebra of the skew filter fractions of the quantum torus that's generated by all cluster variables. And
Can I ask a quick question?
Mm-hmm.
This full rank condition, presumably something you would already meet at classical level if you asked that there be a Poisson structure.
Exactly. That's exactly the condition that if you put a condition that there is a certain Poisson structure that will be compatible with mutation, it's precisely the same mutation. That's absolutely true. So what right now is really unknown is you have everything on the quantum level, you have everything on the classical level with the Poisson structure, and you ask the question when the classical picture is a specialization of the quantum picture. And amazingly, there are very few results for that. There is no general theorem that says that you start with a matrix B tilde that admits such a matrix lambda, and you look at the quantum world and the classical world, and you ask the question, when is the classical one a specialization of the quantum? And it's still like a very simple question, still like a limited number of results.
Wow, I see. So it's so you have a candidate quantization, but you don't know that it's flat.
Precisely. So that's a very funny situation. It's like you know what's going on the classical level. You have the Poisson structure. You have the quantum situation, and you have everything needed, and you still look at the specialization of the quantum algebra is already prepared for specialization. It's defined over the Laurent polynomials in Q, so you don't have to do any integral forms. You specialize that, and until like 2-3 years ago, there were pretty much no results about that. I will say a little bit about like what's going on in that direction. Same thing for the upper quantum cluster algebra, like the upper cluster algebra. It's an intersection of what one would call mixed quantum tori, in the sense that we do invert those variables y1 through ym, and the frozen ones we don't want to invert. Let me just say one word here about not inverting these frozen variables. So let me just come back here to the definition of an upper cluster algebra. And I was arguing that we don't want to invert this for a certain representation theoretic reasons or algebra geometric reasons, that we want certain varieties to become upper cluster algebras. But from a different perspective, we have the Laurent phenomenon that's on the bottom of the slide. And if you decide to invert those variables up here, you will make that upper cluster algebra much bigger than what it should be. And there will be no chance of that equality A equals to U that's on the bottom of the slide. Let me just wait for this black thing to disappear right there. So that inclusion would never become equality because on the right-hand side, you inverted all yn plus 1 through yn. On the left-hand side, you have not inverted them. So that will never become an equality. So that's why we need to keep that mixture. All right, so now, just like I said, there is very limited amount of information of what you can do with specializations of quantum cluster algebras. So when we decided when we were looking at this problem, what should be a quantum cluster algebra at root of unity or root of unity quantum cluster algebra, we thought, okay, we can start with specialization, but there is so little that one can do in order to control in general the specialization that would produce a very limited number of results. So we decided that's definitely not the right way to go. And we thought the other simple thing to define this sort of objects is simply to do mutations where Q is replaced by epsilon. And that's what we're going to do now. So we're going to fix, again, our integer L. We're going to look at the primitive L root of unity square root of epsilon. And we choose a skew-symmetric matrix. The entries of that skew-symmetric matrix is ZL, which is Z mod LZ. And we consider the root of unity quantum torus, which is exactly the one from the previous slide. Instead of Q, we have an epsilon. And because epsilon is a root of unity, when we raise that to that power lambda ij, which is an element of ZL, that's unambiguous. In the sense that epsilon raised to that power lambda is a well-defined complex number. And now we're doing the simple thing. We're just repeating the definition of quantum cluster algebra. We define mutation of a seed by exactly same formula, same integers, m prime and n double prime. So absolutely no rocket science here. But the first thing that we see is that the compatibility between B and lambda now becomes congruence mod L. And because L doesn't have to be co-prime in general to the entries of D, we will have a lot more solutions to this sort of condition. So in other words, the B tilde here doesn't have to be non-degenerate. Again, we define a root of unity quantum cluster algebra by collecting all cluster variables inside the skew filter fractions of this quantum torus and taking the zeta joint square root of epsilon algebra, and the root of unity upper quantum cluster algebra to be again the intersection of this quantum tori, mutated quantum tori, and again they're mixed because we don't invert some of the variables. So far everything is absolutely trivial. The first thing to notice now is that when L is equal to 1, this definition is precisely equivalent to definition of cluster algebras and upper cluster algebra, so we don't lose anything. So if we were to define a root of unity quantum cluster algebra where that root of unity is first root of unity, this will be precisely cluster algebras, without any assumptions on existence of compatible Poisson structures. This simply recovers all cluster algebras. The second thing is that if you look at the cluster algebras that are quantizable, and again, this is not a very well-defined term, what it means for them to be quantizable, but for which there exists a quantum cluster algebra in the sense of Berenstein and Zelevinsky, you want the original matrix B tilde to have full rank. But here, because we have this compatibility modulo L, we will have a lot more quantizations that will exist only at a certain root of unity and not a generic Q. So this is sort of one thing that people wanted very much in quantum groups, to have objects that are discrete, but there is no continuous object that goes with them. So these are like examples of that sort of thing. So we have a certain quantum group at the root of unity without having a generic quantum group. This would occur all the time when you can find a degenerate matrix B tilde, a matrix B tilde that's not a full rank, for which you have such a quantization, but a a quantization in the sense of Bernstein and Zielinski will not exist. And here is one result about specialization. So if you know that the quantum cluster algebra corresponding to B tilde is equal to the upper quantum cluster algebra corresponding to B tilde, then when we specialize the quantum cluster algebra at that root of unity, we're going to produce precisely the original, precisely the root of unity quantum cluster algebra. So this is still an assumption that we have to make here, that AQ is equal to UQ. So a result like this was proved by guys like Leclerc in the case L equal to 1. They have not done that integrally. They work over fields and various other things, but their methods can work in the integral setting. So the thing is, now if we're looking at a cluster algebra with a compatible Poisson structure, we can say that that cluster algebra is a specialization of a quantum cluster algebra if we know that A equals U on the quantum level. So that was a result of guys like Leclerc from about 2-3 years ago. And this whole thing also works at the root of unity. So this gives us a way to construct quantum cluster algebras or root of unity quantum cluster algebras. But one can do this also by hands where a generic quantization doesn't exist. So in general, like to summarize up to this point, we have this notion of a root of unity quantum cluster algebra. It's a very straightforward notion based on the previous ones. And we have certain results that link that notion to other notions that would help us later to construct this sort of gadgets in various situations. Now, what is new in this situation compared to the old situations? Let's do first one example. So A is the first quantized Weil algebra at root of unity over the complex numbers. The generators are X and Y, and the root of unity here is epsilon. So the canonical integral form for this quantized Weil algebra is the one where we look at the subalgebra that's generated by X and epsilon minus 1 times Y. And this is over Z adjoint square root of epsilon. And this has a structure of a root of unity quantum cluster algebra with 2 clusters. The variable Z here is frozen, and it's given by this formula. And when you want to mutate from the first cluster to the second cluster, all that you need to do is take this formula and solve for Y. In that formula, it will give you an expression for Y in terms of X and Z. That will be the mutation formula. If you want to mutate back, then you solve for X, and that will be an expression for X in terms of Y and Z. That will be the mutation formula that gets you from one seed to the other and backwards. So this is sort of a baby example of how this sort of objects can be described in very concrete terms when you work with simple sort of algebras. Perfect. So the first result would be that in this root of unity situation, we still have the quantum Laurent phenomenon. This is now a little more non-trivial than the quantum world because that B tilde matrix doesn't have a full rank, so this requires somehow like new methods. But anyway, that's the result, that the cluster algebra, the root of unity cluster algebra A epsilon, is always sitting inside the root of unity upper quantum cluster algebra. And the second result is that both of them are polynomial identity algebras. This follows from the first result. So not many people know what PI algebras are. So let me just recall the definition. So a PI algebra is an algebra for which there exists a non-commutative polynomial f in the non-commuting variables a1 through an over z, with the property that when you plug in arbitrary elements here, you will get identity equal to 0. For instance, a commutative algebra is a PI algebra when you take the polynomial f of a1, comma, here is a comma is missing, comma a2, equal to the commutator of a1 and a2. So commutative algebra is an algebra that's described by the property that the commutator of every two elements vanishes. PI algebras have been studied quite a bit in ring theory. The generalizations of this picture that appeared at the beginning, where an algebra is module finite over a central subalgebra. And again, these people, Procesi, Arti, and Kaplansky, have proved a lot of results about the representation theory of such an algebra. That's good. And next comes the key property for root of unity. So we're going to denote by C of B tilde the subring of the root of unity quantum cluster algebra, which is going to be generated by the L powers of all cluster variables Y.
Sorry, Milen, can I interrupt you?
Mm-hmm.
So you claimed, can you go back one slide?
Mm-hmm.
So you're saying that they're polynomial identity algebras. Can you say a word about what polynomials those are in this case? I mean, presumably this is meant in an explicit way, right?
Thank you. Absolutely. So one can prove out of result one that the algebras A and U can be embedded in a polynomial algebra of some very large size over a commutative algebra. And then if you look at a polynomial algebra of size n over a commutative algebra R, so the first question that people asked in the 50s and 60s is what are the identities that are satisfied by the matrix algebra over commutative algebra R? So this is the so-called Amitsur-Levitsky theorem that says that the minimal identity that's satisfied by the algebra of n by n matrices over commutative algebra is a certain identity of degree 2n. And for instance, look at this identity. You can think that A1 and A2 are matrices of size 1.
Yes.
And then you get an identity of degree 2. So if you look at matrices of size n by n, then they're going to satisfy an identity of degree 2n, and that identity that's satisfied by the matrix algebra is the Amitsur-Levitsky theorem. There were many proofs. For instance, Constant had a proof of the Amitsur-Levitsky theorem using representation theory. So that was quite popular subject in the 60s and 70s to reprove the Amitsur-Levitsky theorem.
So such an identity could be, for example, this, because I remember once Procesi talking about Cayley-Hamilton identity. So such an identity could be.
Yeah, that's slightly different. That's a slightly different identity. So the Cayley-Hamilton identity is an identity that says that if you have an algebra with trace, then we want to impose the identity that every element will satisfy its characteristic polynomial. And that is the definition of a Cayley-Hamilton algebra. And for instance, an example of a Cayley-Hamilton algebra will be the algebra of n by n matrices. But what is an identity that involves not only elements, but also their traces? And here, the definition of a PI algebra, you don't want the traces in the identity. So if you allow the traces in the identity, the Cayley-Hamilton identity will be an example of an identity that's satisfied. Without traces, it's the one in the Amitsur-Levitsky theorem.
But do you have some kind of trace form that's natural in this situation?
Not yet. So that's a great question. That's a great question, and we will talk a little bit about discriminants, but those will be in a certain concrete situation. So that's a great question. So yet there is no natural trace in this situation.
Because actually, I find that the theory of this Cayley-Hamilton identities, etc. If you have this, relations with the trace, they're much nicer somehow than these polynomial identities.
I have much worked with Cayley-Hamilton algebras, and we are looking for a natural way to prove. So the way this game here goes is you prove that your algebra is a maximal order in a central simple algebra. Then you apply Posner's theorem in order to embed certain localization, and then you get the existence of a trace for free. So the game that people play in this situation is just to prove abstractly that your PI algebra is a maximal order in a central simple algebra, and that gives the trace for free. But we don't have that result yet in this generality. So that's a great result. So the question here is, can you prove that the algebra A epsilon of B tilde is a maximal order in a central simple algebra? Then it will become Cayley-Hamilton algebra automatically. So yeah, that will be great to have. Perfect. So here comes now the next the first very like interesting result is look at the subalgebra of this root of unity quantum cluster algebra that's generated by the L powers of all generators. And then also we can look at the zeta joint square root of epsilon subalgebra that's generated by exactly the same elements. And we will call this second algebra the de Concini-Katz-Procesi subalgebra of the root of unity quantum cluster algebra. And the results are that if L is a primitive L root of unity, if epsilon is square root of epsilon is a primitive L root of unity, L is odd and is co-prime to the anti-symmetrizing integers of the principal part of B tilde. The C epsilon of B tilde, what we called here the de Concini-Katz-Procesi subalgebra, is always a central subalgebra of our original algebra, original root of unity quantum cluster algebra. And furthermore, it's isomorphic to the underlying cluster algebra. And if we look at the subalgebra that was generated by those gadgets, but over zeta joint square root of epsilon, that will be simply an extension of the cluster algebra where z is extended to zeta joint epsilon. So in other words, we have the quantum object, and inside the quantum object, we have this central subobject that is canonically isomorphic to the classical object. So it's a nice situation in the sense that before in quantization, the classical object is always realized as a factor of the quantum object. And here the classical sits in the center of the quantum object, and when we extend the scalars, we simply have to extend the classical object to that base ring. For instance, people in cluster algebras look a lot at the exchange graphs, and those exchange graphs are like how the seeds are related to each other. So one thing that you can get out of this theorem is that the exchange graphs in the two situations are isomorphic because you have the classical object sitting inside the quantum object, and you can somehow use this to prove this isomorphism. So now let's go to the picture of the Concini-Katz and Procesi. So we take any symmetrizable Katz-Moody algebra G, any vowel group element L, primitive L root of unity square root of epsilon, just under the assumptions that the Concini-Katz-Procesi worked. And the first result is that the integral quantum Schubert cell algebra is isomorphic to a certain root of unity quantum cluster algebra, which can be very, very precise. And under this isomorphism, the de Concini-Katz-Procesi central subalgebra corresponds to the central subalgebra that we constructed. One thing to note is that from the cluster world, we have two completely different objects. One is the central subalgebra that's defined over zeta joint square root of epsilon, and the other is the subring. So the Concini-Katz-Procesi were actually seeing from Lie theoretic works this central subalgebra, but they have not seen in their works this central subring that is sort of an integral form of this central subalgebra. So in this, from this cluster theoretic perspective, we're actually having both. So the central subalgebra is isomorphic to the one of the de Concini-Katz-Procesi, but inside this central subalgebra, we also have a canonical ring for which the central subalgebra is just an extension of the ring from Z to zeta joint epsilon. And where do we want to go from this? So the Concini-Katz and Procesi have a conjecture from the 90s that if you look at each irreducible representation of this algebra, it should have dimension equal to L raised to power D over 2, where D is the dimension of a certain symplectic leaf of a Poisson manifold. And basically the idea is maybe this theorem will be helpful in order to prove this conjecture, because the whole point now is that you study the representation theory of these quantum Schubert cell algebras, and they're sitting inside many different quantum tori. So if you take an irreducible representation of your algebra, you can localize that representation in many different ways in order to make it a representation of the quantum torus. So if you somehow adjust the quantum torus appropriately to this symplectic cliff, maybe you'll be able to see exactly this, this sort of conjecture, because the irreducible representations of quantum tori are very well understood. So somehow this flexibility of not having only one quantum torus, but infinitely many ones, we hope that that will be somehow key in seeing how one can resolve this conjecture. Perfect. So now I have results about discriminants in this setting.
Milen,
Yeah.
can I ask another question? This conjecture wasn't maybe a special case of the conjecture proved by Kremnitzer and a collaborator?
That's the Kremnitzer and collaborator. That is about the two different
Backelin, I think, was the collaborator.
Backelin, yes. There are two different conjectures. One is about the representations of the quantum group UQ of G, where G is a finite dimensional Lie algebra at root of unity. And that conjecture is that L raised to power symplectic dimension of symplectic leaf over 2 divides the dimension of the representation. And that is somehow the way people think about that conjecture, is that that is like representations of restricted Lie algebras, of semi-simple Lie algebras. And this is like related to representations of universal enveloping algebras of solvable Lie algebras. So somehow the situation is different, like in one case and in the other. So the one that Kremnitzer and Backelin were working on is the whole UQ of G, not the quantum Schubert cell. And to the best of my knowledge, that's still a very problematic proof. It hasn't been published anywhere. It's been on the archive for more than 15 years now. So I'm not exactly sure about the status of what people think about that proof, but it's been on the archive since around 2005. Right. Yeah. So they had papers on quantum, on quantum D modules, and they somehow used those in order to resolve the conjecture, but that hasn't been published yet. But this is somehow a slightly different situation. So should I go until 3:50, or there should be like 10 minutes for questions? Should I stop now, or I have 8 more minutes?
Well, actually, you have more like 12, 13.
Perfect.
Then we'll take some time for questions.
Great. Excellent. So the next thing I wanted to tell you is we still don't know how to handle the representation theoretic side, but there are these number theoretic invariants of PI algebras called discriminants, and those we can somehow resolve in this full generality. So let me recall very quickly the discriminant of a number field. So that was defined by Dedekind in 1871. So you take a number field K, which is by definition a finite field extension of Q. So it's K is isomorphic to Q to the n as a vector space. Inside K, you look at the ring of integers. That is isomorphic to Z to the n as an abelian group. And now we have a canonical embedding of the ring of integers of K to the algebra of n by n matrices over Z. And it's the most straightforward thing that you can imagine. OK acts on itself by multiplication. So therefore, each element of OK is going to induce an automorphism of this free abelian group, and also encode it in the n by n integer matrices. And then you can compose this embedding with the trace function on n by n matrices. And this is called the trace function of your number field. The discriminant of the number field introduced by Dedekind is the determinant of the traces of yi, yj, where you pick up any z basis y1 through yn of that ring of integers. And it's an easy exercise that this is independent on the choice of basis. So the discriminant plays a sort of very important role in algebraic number theory. It enters in the residue formula for the Dedekind zeta function of k. It measures which prime numbers ramify and various kind of things like this. So people in PI algebras realize that they can extend this, but in order to extend this, you need to have an algebra with trace, just like Harms was asking. So we need an algebra with trace in order to introduce this notion of discriminant. So a trace function on an algebra R is a function that goes from the algebra R to the central subalgebra Z. Usually you want R to be modulo finite over Z, which is cyclic and which is Z linear. So here is, I shouldn't call this an important case. This is maybe the simplest case when R is isomorphic to Z to the N as a Z module. So it's a free module of finite rank. Then we can play exactly the same game like Dedekind and map and construct a homomorphism from R to the algebra of n by n matrices over Z, and we can compose that with the trace to Z. So this is called the trace function of your algebra R. And if you are in this free situation, if R is free module over Z, then the discriminant of A is again the determinant of these mixed products, and it is defined up to a unit of Z. So it's defined up to an associate, like we teach in algebra 2. It's an element of the central subalgebra Z defined up to an associate. Perfect. If you don't have the freeness, then you don't have a single discriminant, but you have a bunch of discriminant ideals. So those are also of interest, and there has been quite a bit done on the structure of discriminant ideals too. So here is the formula. So if A epsilon of B is a root of unity quantum cluster algebra, and now we have an assumption that it's a free module over the central subalgebra. So obviously this is a restricted situation. It's not going to hold all the time. Then we can look at two things. We can ask what is the discriminant of the algebra A epsilon of B tilde over the central subalgebra, the one like in de Cuncini-Katz-Procesi, or we can ask what is the discriminant of the big algebra over the subring that was isomorphic to the classical cluster algebra. And the theorem says that they are all certain integers times powers of the frozen variables. I don't have much time to talk about like what appears here, but somehow the key point is we do want to compute discriminants because they tell us a lot about the representation theory of these algebras and also about other invariants. And in these two formulas, we basically, with these two formulas, we can basically quickly compute discriminants of these quantum cluster algebras at roots of unity when we have this freeness assumption, because the integers in front are certain concrete integers, and the only thing that we have to determine is the powers of Z. So here I'm going to finish with a couple of formulas. So first, if we look at the first quantized Val algebra at the root of unity, it's the algebra generated by XY with this relation. It's a free module over its full center. This is the full center. And our theorem is going to say that the discriminant of the algebra over the central subalgebra is this power of L times a certain power of Z. We don't know what power, so the theorem doesn't tell us what the power is. We can run easy filtration arguments, and for a couple of lines, you get that the power is equal to L minus 1 times L. And before this work, there was a whole paper of Chen, Yang, and Zheng that proved this formula, but it's a pretty long paper. It's like 20, 30 pages paper in algebra and number theory that basically proved this formula. So this is a one application of the theorem where it gives a quick proof of the formula for just a couple of lines. And the last thing is like, if we look at this de Cuncini-Katz-Procesi subalgebra Z epsilon of the integral quantum Schubert cell algebra U epsilon of n minus of W, it's isomorphic to the coordinate ring of the corresponding Schubert cell. Again, everything is done integrally. So this is a Schubert cell in the corresponding flag variety for the Katsumoto group G. So here G mod B plus is the flag variety, and this is the Schubert cell in the flag variety. So if I want to compute the discriminant of this algebra U epsilon of n minus W over the central subalgebra, so that was sort of one of the open problems about these quantum Schubert cell algebras, I have to name an element of this coordinate ring. So it's going to be a certain function on the Schubert cell. And we can apply the previous theorem and run, we can apply this theorem. So we already know that these quantum Schubert cells are special cases of these roots of unity. So we can apply these formulas, and all that we need to determine is what are the powers of these frozen variables. And the theorem tells us that it's also done by some easy, so in this case, it's grading arguments. It's just arguments with grading. That powers are simply L minus 1 times L raised to power n minus 1. And the corresponding frozen variables are certain functions on the Schubert cell, which are just given in terms of generalized minors corresponding to the ith fundamental representation and the extremal weight vector W of omega I. So that's the formula for these discriminants in this generality. And I'm ready to stop here. So thank you.